In this video, I will be solving some rotational dynamics problems. The main formula to work with is Newton's second law in rotational form. So as you know, this is the main standard Newton's second law. Net force is mass times acceleration. So in rotational motion, this will be translated to net torque is moment of inertia times angular acceleration, as you know. So, force will be replaced by torque because torque plays the same role as force does in translational motion. Similarly, moment of inertia plays the same role in rotational motion as mass does in translational motion, and same thing with alpha and a. So this is the main formula to remember. So let me pick some random problems to work with. So the first problem to get started with is this simple problem. you know so here, as you can see, mass is tied with a string, and it is wrapped around a cylindrical cylinder of radius r, and as you release the bucket, its action was the linear acceleration produced and the tension in the string. Okay, so clearly this is not a free fall. So then what would be the linear, the vertical acceleration of the bucket? Let's get started. So the first thing is, you need, again, when you deal with force, torque, you always will have to deal with the free body diagram. So I'm just gonna first start it with the free body diagram. So free body diagram for the bucket, falling mass bucket, okay, is going to be like this. So bucket is this and is pulled up by tension. So just keep in mind that the tension develops here both ways, equal and opposite, Newton's third law. But for the bucket, if you are drawing the free body diagram and Newton's second law for the bucket, you need this tension, because tension is always a pulling force, and of course its acceleration is downward, and that's mass. That's the free body diagram for for the bucket falling mass. So then you can apply Newton's second law. So I'm gonna apply Newton's second law. So it says sum of the force, net force in y direction is mass times acceleration. Sum of the force is t minus, or I'm just gonna make the greater force as positive. Since mg has to be greater than t because it's accelerating downward, I'm gonna make this downward as my positive axis. So you can do t minus mg. So then it's going to be mass times acceleration, right? So then tension will be mg, right, minus me. Equation number 1. You can't solve this completely because you have two unknown variables, tension and acceleration, you don't know. So you need one more free body diagram. Now I'm gonna do the free body diagram for the rotating cylinder. Okay, so cylinder, now just 2D picture. So it's being pulled by this tension, right, and it has a radius of r, and radius makes 90-degree angle to calculate the torque. And for the rotating disc cylinder, the Newton's second law, right, in rotational form I just explained, is net torque is I alpha, right? I is the moment of inertia of the cylinder, which we know. So net torque here in this example is, net torque is always Rf sine theta. The magnitude of the torque is always Rf sine theta. Is I is 1/2 mr square, which is the moment of inertia for a solid disk or solid cylinder. It's given on the formula sheet. And alpha, you have to convert the angular acceleration to the linear acceleration. So you can compare with equation number 1, a over r, and in this case a over radius, right, because string is attached to the circumference and then radius is just a big R. Okay, so R is big R, F is tension, sine of 90 degree, this A over R. So 1 R will cancel out, is 1/2 MRA. So again 1 R will cancel out, and sine 90 is 1, so tension is 1/2 mass times acceleration. This is, remember, this is mass of the cylinder and this is mass of the bucket. There's big capital M and lowercase m. Be careful. Now just put the tension. You have to eliminate tension from equation number 1. Put the tension as mg minus ma is 1/2 big mass, which is mass of the cylinder, and then you solve for acceleration. That's it. So mg is, I'm factoring the linear acceleration because that's what we're solving. Mass times gravity divided by m plus 1/2. So that's the linear action, and then you can put all the values. All these masses are given, right? So you can put, and then you can find the acceleration of the bucket. And to find the tension, then you can use equation number, again this, let's say equation number 2. For tension is 1/2 mass times A is now acceleration is mg m plus 1/2 m, and then you can just leave it like this. This is the tension. So this is the vertical acceleration produced on the bucket, and this is the tension in the string. So that's how you solve. You will always be combining the standard, Newton's second law in translational motion with the you know the rotational dynamics. Okay, so the next problem is similar, right? Something like that. Mass, the hanging mass m2 is connected to the light string, and then this is wrapped around the circumference of a cylinder or pulley, but in this case a brake is applied, so there's some frictional torque acting on the system. So there are two types of torque produced by the tension, hanging mass, and torque produced by the friction. So it's asking the same question: what's the magnitude of the linear acceleration of the hanging mass as it, and the tension in the cord? Okay, and then the numerical value. So first let's solve in terms of symbols algebraically, and then you can put the all the values. So again, you need free body diagram. So first the free body diagram for the falling mass, which is m2, and remember again, this tension will develop everywhere, like pressure, right? Tension is everywhere and equal and opposite, and but for m2 is accelerating downward, so you need this tension is always pulling, and this is the acceleration. Okay, so Newton's second law is, I'm going to apply Newton's second y direction. So the first, I'm going to make bigger force as positive. m2g minus t is m2a, and tension is again m2g minus m2a. Let's call equation number 1 because we can't solve this because there are two unknown variables, t and a. So you need one more free body diagram. So free body diagram for the pulley or cylinder. So now here, the cylinder is acted by two types of torque. Okay, one is from the tension, is pulling, right, is the radius, and one is from the brake. Brake is right here, right? Brake is right here. So it's pressing like this. So it also makes 90-degree angle. So it's the frictional torque. You can say it's a frictional torque because brakes apply the friction and it applies negative torque. Okay, so again the net torque is I alpha. So the net torque now is the torque produced by the tension in the string and torque produced by the brake. So you have two things. So so T R times T sine of 90-degree, right? And I'm again making the bigger torque as positive. Negative, the brake will apply negative torque because it is trying to slow it down. So I'm gonna apply the frictional, the radius is same and frictional force, and but it also makes 90-degree with the friction. Okay, is equal to I times alpha. So I'm just gonna simplify that now. The radius is common, so T minus frictional force is moment of inertia again is 1/2 mr square, because that's the moment of inertia for a solid disk. It's given, and alpha you have to convert into linear acceleration, which is a over r. R will cancel out, this one r will cancel, so it's again becomes a simple equation, is equal to frictional force plus 1/2 ma, and you have to now eliminate tension. So right, you have to eliminate the tension. The frictional force is given to you, so it's m2g minus m2a is force of friction plus 1/2 mass of this times acceleration, and then you just need to now solve for a. M2g is minus force of friction is m2 plus 1/2 a, and the acceleration is m2g minus force of friction divided by m2 plus 1/2 m. So that's the acceleration. Okay, that's the acceleration of the falling mass. And now all the values are given if you want, so you can put all the numerical values. So mass is 0.109. So I'm just putting the frictional force is 0.161 newtons. All the values are given. So 12 plus 1/2 is 700 gram. So the linear vertical acceleration is 1.19 meters per second square. It's much less than free fall 9.8, right? And it makes sense because there's brake as well. And then you can do the same thing. You can now put the value of a in one of this equation, either here, or equation number 1 to find the tension. Okay, so that's how you find. So the next problem is again adult machine. This is called adult machine. The only difference is now the pulley has some mass. Pulley is not massless as we used to do in our force problem, two body force problem in the beginning. So pulley has some mass, so that's why it has some moment of inertia. So then you need to consider moment of inertia of the pulley, which is a solid disk, into consideration to solve this problem. So the question is, what's the acceleration of the system? So let's put some symbols. So let's call this M1, then let's call this M2, and the radius of the pulley is R, and its action was the acceleration of the system. Okay, both two masses, since they are connected system, they must have same acceleration. So what's the acceleration of the system? That's the question, right? And you can put all the numbers here. Numbers are first. Let's derive the problem algebraically. So again, here, uh, first of all, now tension in this string both sides won't be same. Why? Because since this is a bigger mass, it's rotating this way, right? It's rotating clockwise like this. So tension in this string must be greater than tension in the left string. Otherwise, the net torque will be same, and then it won't be rotating. So the first to keep in mind that the tension won't be same now. On the given string, tension is same, but this is different from the other side. That's called T1 and T2. So free body diagrams for unit 3, free body diagram now for M1, M2, and for the pulley. So for M1, right, this is M1 is falling, M1G, and tension must be less than, right, for M1 because its acceleration is that way. So then if you use Newton's second law, M1G minus T1 is equal to M1A. So tension T1 is M1G minus M1A. Let's call equation number 1. So free body diagram and Newton's second law for M2, right, which is smaller mass, is moving up. As it falls down, it moves up. So it's a again a adult machine, and with but this pulley has some mass, so you can't ignore moment of inertia. So for M2, the free body diagram will be something like that. Now tension will be greater than M2G because why? Because you have acceleration in this system. So again, making the greater force, stronger force as positive, T2 minus M2G is M2A. M2A, let's call equation number 2. And one more. So free body diagram for the pulley, right, and apply the torque. So this is like this. So T1 and T2 is pulling that way, right? T1 must be greater, but they make 90-degree angle. So it's trying to produce rotation that way. It's trying to produce rotation that way, but net torque tau is I times alpha, right? And net torque is now RF sine theta, sine 90 is 1, so R times T1 minus R times T2. I'm again making the greater torque as positive. Um, don't worry about the clockwise and counterclockwise right now. So I is, again, let's write down that. So R is common factor, T1 minus T2 is 1/2 mr squared. That's given. That's for the pulley, solid pulley. A over R because the string are attached to the circumference, right? And now you can, radius is gone. So T1 minus T2 is 1/2 m times A. Now you have to eliminate this both T1 and T2 tensions from equation number 1 and 2. And then you're done. You can solve for acceleration. So what is T1? T1 is M1G minus M1A. T2 is, what is T2 from equation number 1? M2G plus and minus M2A is 1/2. And then that's it. So you solve for A. So M1 minus M2G common factor, and you put all A together. M1 plus M2 plus 1/2 big mass, which is mass of the disk is. And finally, the acceleration of the system is M1 minus M2G divided by M1 plus M2 plus 1/2 mass. So that's your final expression, you know. Okay, so that's how, this is the formula for acceleration. Okay, and then since all the masses are given, the numerical values are given, you can just put the masses and then find the actual numerical value. Okay, the next problem is also similar to the modified adult machine problem, just like we did in the force problem, Newton's second law problem, But the only difference here is now pulley is not massless. Pulley has some mass. So if the system is released from rest, the question is what would be the acceleration of the system? Both masses must have same acceleration, right? Because they are connected by ideal string. And the question is, what would be the acceleration of the system? Okay, next problem is similar, again, two masses, but one mass is lying on a horizontal table, one is falling mass, and so it's just acting again the acceleration of the system. And this pulley has some mass, its radius is r, its radius is r, and it has moment of inertia, so you can neglect the mass of the pulley. So what's the acceleration? Again, let's symbolize everything. M1, M2, the pulley has, let's say, big mass M, and this has acceleration that way. This has acceleration must be same because they are connected by ideal string, and so there's no friction on this table, say, for simplicity. And tension will develop. Again, this tension will be different, so let's call this is T1 tension, this is T2 tension, right? Again, you need three equations. So for free body diagram for M1, the falling mass is M1g because it's accelerating downward, so T1. So Newton's second law would be M1g minus T1 is M1a, right? And then T1 is M1g minus M1a, equation number 1. So I'm going to do the same thing for M2, which is on horizontal floor, but there's no friction for simplicity. For M2, the Newton's second law says, first let's draw the free body diagram. It has only one force acting, which is tension T2, and acceleration is that way. There's no friction. If there's friction, you have to add that way. So T2, Newton's second law is the only force is T2 is M2a. Let's call equation number 2. Now you need one more free body diagram for rotating system, which is for the pulley. For the pulley, now pulley is rotating, so you need Newton's second law in rotational system. So is net torque is I times alpha. Net torque, there are two torques. Torque produced by this tension, which is greater than this torque produced by this, right? Because this is moving downward. So RT1 sine of 90 is 1 minus is opposite torque. Our radius is same for both, right? Is 1/2 mr square, that's the moment of inertia, times a over r. They're all same. And r is common, T1 minus T2 is 1/2 mra. R will, so it's radius independent, so T1 minus T2 is 1/2 mass times acceleration. And then you have to eliminate tension T1 and T2 from equation number 1 and 2. So let's put T1 is M1g minus M1a, minus T2 is M2a, is 1/2 m mass of the disk. So M1g is M1 plus M2 plus 1/2, and I'm just putting all together. So acceleration of the system is M1g divided by M1 plus M2 plus 1/2. So okay, that's the formula for acceleration of the system, right? And if the masses are given, you can just plug the numbers in and then find the acceleration. And once you find the acceleration, you can find the tension from these equations, the numerical values, if numerical values are given. Right. So in this animation, I will show you how to use the rotational, you know, rotational version of work energy theorem. As we know, we've been using this work energy theorem a lot in the previous chapter. The work done by force is equal to change in kinetic energy. The force could be a variable force, or force could be, you know, a constant force. So, but in this example, a rod is pivoted at one end, and if you release from rest, it will gain some angular velocity as it falls. And here torque is not constant, as you can see, because the angle between the force of gravity here, which act at the center of mass, and the position vector, the angle between force of gravity and the position vector is constantly changing. So that means torque is not constant. So you have to do the integration of the torque, right, with respect to theta, which gives you the work done by torque, is has to be equal to change in rotational kinetic energy. This is rotational kinetic energy, 1/2 I omega square, which is pretty similar to our standard equation of work energy theorem. And then you should be able to solve the problem, using rotational version of work energy theorem. Okay, one more problem. This problem is something like that. This is a rod or a bar or thin rod, pivoted at one point. So initially it's kept horizontally like this, and if you release that, it's acting. What's the angular velocity? As it gets vertical. As it gets here. So something like that. And the first question is, what's the torque on the rod when it makes an angle theta? So for example, at any position, so right, this is the position of the rod at theta position, right? What's the torque acting on that? So that's the first part, and that's really easy, because the first of all, for the rod, right, it's a uniformly distributed mass, rod. So the force of gravity acts right at the center of mass of the rod times gravity, right? And if this is theta, and this is your position vector r. So you just do rf sin theta, So torque on the rod, right? The net torque on the rod is just rf sin theta. We're calculating magnitude. So r is, because since the force act at the center of mass, right? So the r is half the length, right? Its position vector will be half the length. The magnitude will be half the length. Force is just mass of gravity and sine of theta. That's the magnitude of the torque. That's it. So at any position, when it makes angle theta, right, the rod is experienced by this torque, and because of that torque, it actually rotates. And this theta is changing continuously, right? Okay, and one more thing is, because torque is a vector quantity, what's the direction? And then you have to use right hand thumb rule. Right hand rule. So it's like this. So you point your fingers towards r position vector, call your fingers towards the gravity force of gravity, like this, and point. This thumb is downward. So either you can say negative z, right, or you can say it's clockwise. Clockwise is negative. Negative z is downward and perpendicular to the plane of the paper. Okay, that's the first question. Second question is, now find the equation, right, for the magnitude of the angular acceleration produced. So because of this torque produce, remember, force produce acceleration, torque produce angular acceleration. So angular acceleration, right? So what's the angular acceleration? So then you just use Newton's second law. Net torque is I alpha. This is the Newton's second law, right? In rotational form. So net torque we already know, L over 2 mass times gravity. So it's just acting the magnitude. So don't worry about the sign. And I is, remember this, the moment of inertia about when it is pivoted, right? So there's a separate chapter on this, actually calculating the moment of inertia. So if you pivot at one end of the thin rod, its moment of inertia will be 1/3 ml square. L is the length. Okay, moment of inertia depends on where you choose the axis of rotation, where you choose the point of pivot. So at one, if you pivot here, its moment of inertia will be 1/3. So 1/3 ml square alpha, and that's it. So that's your alpha. So alpha, which is the angular acceleration produced for the rod, will be then 3/2 mass will cancel out, right? And 3/2 g sine theta divided by L. So I forgot, yeah, one L will cancel out, L. So that's your answer. That's the angular acceleration produced. So that's the easy way. Just use Newton's second law in rotational form. But there's another way to calculate the same angular acceleration. So you can use work energy theorem, in rotational dynamics, which is this, right? If you remember. Um, so work energy theorem in rotational dynamics is this. The work done by torque. This is the work done by torque, which is nothing is torque times the angular displacement, right? Just like similarly f dx. This is f x dx, right? It's the work done by torque is equal to, now this is the change in rotational kinetic energy. Rotational kinetic energy is 1/2 omega square, 1/2 I omega square. So we can do the same problem B using slightly different approach. So I'm gonna quickly show that. So it says the work done by torque, which is d theta torque times the work done by torque is, now theta 1 to the initial angle to final angle is 1/2 I 1/2 I initial. So this is similar to fx dx, right? Is 1/2 mass v final square minus 1/2 v initial square. So similar. This is the work energy theorem, right? So we're going to use here this. So torque, as you know, torque is, we have already calculated. Torque is Lmg sine theta 1/2, right? Times d theta. But you have to put negative sign here because this torque pivot point, this is a clockwise torque, right? Is negative g, direction is negative g or clockwise. So, and angle, initial angle is 90 to some angle 0 degree, because when it gets here it makes 0 degree angle, right? This theta will be, initially this angle is 90, but when it gets vertical its angle is 0. So, and is equal to right hand side 1/2 I omega final, where we're finding this final omega, okay? And initial is 0 because it was held, it is held horizontally initially, so it's at rest. So then you do this, right? And so negative Lmg over 2, so integration there, so 90 degree to 0 sine theta d theta is 1/2. This is moment of inertia again is about this pivot point 1/3 ml square omega final square. Okay, and you can see you have to do integration because torque is not constant here. I forgot to tell you, because this angle theta is constantly changing as it falls. So you have to do integration to find the total work done by net torque. So this is going to be negative Lmg over 2, and this is negative, the integration of sine theta is negative cos theta. You have to put the limits, right? This is 1/6 ml square omega final square, and then if you put the limits, and then after that you will get the final angular velocity is given by this. Okay, this is the final angular velocity when the rod gets vertical. Okay, that's how you can solve.